Okay, this is part 3 of the soft matter introduction. And in these few minutes, I'm going to tell you about one of the tools of theoretical physics to deal with phase transitions and different types of soft matter. This is really based on Landau theory, which has been already mentioned previously. And before we get into Landau theory, let me remind you that universality really means that, or the existence of universal classes, that we can take the simplest possible model to investigate the behavior near a phase transition. And so for scalar order parameters, one of the simplest model is really the Ising model, where we have spins that interact and ferromagnetically, so they tend to align, but the thermal energy tends to disorient the spins. In dimensions d2 or more, there is a critical temperature above which the system is paramagnetic, so the total magnetization is 0, and below Tc, the system, in the absence of magnetic fields, exhibits spontaneous magnetization. So this is a typical example of a critical point of a system with a scalar order parameter, which in this case it is the magnetization. This is the quantity that becomes non-zero below the critical temperature. In statistical mechanics, if I wanted to treat this system, calculate the equilibrium properties, I would calculate the partition function, which is here, and this is just a Boltzmann factor of the interaction of the spins divided by kT, and the same interaction of spins with an external field. And the equilibrium free energy would be just the log of Z multiplied by kT with a minus sign. So this is the StatMech program to calculate the equilibrium properties of this system, including, of course, the existence of a critical point. However, that sum is very difficult to carry out, especially near the critical point where we've seen fluctuations are large and they correlated, so I cannot really do very much. So analytically, except in 1D and in 2D. However, there is a theory which is very general, and it really is more like an approximation, but can be applicable to a wide range of systems which have similar symmetries or types of order parameter. This is Landau theory. And the reason why I started with the ferromagnetic transition is because in Landau theory, the first thing that we need to know is what is the order parameter. We have to define an order parameter. And this is sometimes not very clear, but in the ferromagnetic transition, it's clearly the magnetization. So in terms of this magnetization, I can write the previous expression for the partition function, now dividing it in two terms or two sums, one of which is I fix the magnetization and then I sum over all spin configurations compatible with this fixed magnetization of the same Boltzmann factors. Okay, so this is one of the ways of doing the sum. It's just a different way of writing it. Of course, now that we've written it in this way, we're going to exploit the fact that the inner sum over the Boltzmann factor of the interactions, which is here, can be interpreted as the partition function of a system with a fixed magnetization M. And in turn, this may be used to define generalized free energy F as written below in this equation. This free energy is not really the equilibrium free energy, but a generalized free energy. And for very large number of spins, These function may be assumed to be extensive as well, like the thermodynamic counterpart. And we can then write that the equilibrium free energy is then written in terms of this little f, which is the free energy density of this f. Okay, so this is just manipulating and renaming some of the quantities and the sums. And the thing is, now we still need to do the sum over m, the various magnetizations, and we still need to find out what this little f is. Okay, so in a way, the problem of doing the sums still remains. And we're going to do this in two parts. But before we do that, even though this is not the most rigorous way of introducing coarse graining, this can be viewed as a coarse graining procedure, where rather than writing the equilibrium properties in terms of the microscopic spins, we're doing it in terms of, I call it mesoscopic here, although this magnetization is really a calculator of the whole system. But if I was doing this in a more sophisticated way, rather than fixing m, I would just average over a few spins, and this magnetization would change, would be a statistical field. And rather than a sum over m, I would have a functional over the different possible forms of m of r. However, for what matters, I don't need all that sophistication, but that would be the correct way of doing it. And in that sense, m would really be mesoscopic. But this is the idea of coarse graining. Okay. So now we still need, however, we still need to do this sum, and we still need to define little m. To do that sum, we're going to use a trick, which is actually a very good approximation for very large systems away from the critical point, which is to approximate the sum over m by the largest term here. And of course, this is an exponential. So the largest term is the one that minimizes this expression in brackets, because there's a minus sign here. So if I get the minimum, because it's multiplied by a minus sign, this will give me the maximum term here. So I'm going to approximate the sum. And for that, I need to minimize that function with respect to m. That defines the maximum term. And then at equilibrium, I can write the equilibrium free energy per spin as the function little f as a function of m0, which is actually the value of the magnetization that maximizes the exponent in the equation in the previous slide. Okay, so now we've done the sum, or at least we've approximated the sum, but now we still need some way of calculating or guessing little f. And this is what we'll do next. Because this free energy density is supposed to apply close to the critical point where m is small, it's possible to expand, or we'll approximate little f by an expansion in powers of the magnetization. There is a term which may be a temperature dependent term that does not depend on m, and then we have even powers of m. And the reason why we have even powers is because in this system there is a symmetry between up and down, so we cannot have terms that are odd, like m to the cube and so on, because that would mean that the free energy would change if I change the orientation of the spins. So it's not compatible. So symmetry comes in here. And we still need to do something about these coefficients, because at the moment we know they're functions of t, but they're still not, they're still arbitrary to some extent. So what we'll do is, again, we're close to the critical point, so we can expand the first coefficient around Tc, and we can consider the second one temperature independent. It has to be positive for stability reasons, but I cannot really go into much detail. Nevertheless, we managed to write down an expression for little f, which in turn will give me the equilibrium properties, as I said before. And now all I need to do to calculate the values of the magnetization or of the order parameter at a given temperature, all of this is in zero field, I need to minimize this function. Okay, so here it is above TC. It has this simple parabolic shape with a minimum at zero, which is consistent with the fact that I have a paramagnet. Below TC, I have a double well function. So there are two minima and one local maximum. And these two are symmetrical. They correspond to magnetizations positive and negative. They're equivalent in terms of the free energy, but if the system magnetizes spontaneously, it will choose one of these. This is why symmetry breaking is applied to this type of transition, and the values of these minima can be calculated very easily by looking at the expression above and taking calculating the minima of the function. So we obtain something that we knew already, that above TC, the minimum is unique and it's zero, it's a paramagnet. Below the critical temperature, we have two symmetrical solutions that correspond to a value, non-zero value of the magnetization, and that varies or vanishes near the critical temperature as from below as a square root. So this is here the order parameter. This is zero above TC. This is all at H, magnetic external magnetic field zero. So far, so good. And this is just a full representation of the phase diagram, and now also the behavior with the magnetic field. But I will not go through it. If you look at this slice here, this corresponds to this picture in this slide. Okay. Just before I move on, I would like to point out something that I've already mentioned, but it's also borne by this theory, because magnets and fluids, at least uniaxial magnets and fluids, they have the same type of behavior, and they have very similar looking phase diagrams, although a fluid is not completely symmetric. But around the critical point, I can look at it, and of course, I can restore some symmetry. And a fluid and a magnet in this description have exactly the same type of behavior, which is also borne by experiments. And in fact, what this theory does not predict accurately is these exponents. So I said here, the exponent that goes with the order parameter is 1/2, and in reality is more like 1/3. But we've done approximations when deriving the Landau theory, and now it is well known that these differences are related to the neglect of those fluctuations. But this is not the point to really say much more on that. Okay, I'd like to finish these by showing that the ideas behind the simplest Landau scalar order parameter theory can be extended to describe more complicated types of order. In particular, we talked about liquid crystals. We said nematic is the simplest ordered liquid crystalline phase, and in a nematic I have particles that orient along an axis, and this is not polar order, it's not a vector, because these molecules don't have an arrow. I mean, the orientations cannot distinguish if the molecule is up or down. So the proper order parameter to describe this is not, it's not just a vector, but it is something like a second order tensor. And this tensor has other properties because this phase is uniaxial, only has one axis. And again, I don't have much time to go about it, but it's not completely obvious that this is the order parameter for the nematic phase, but from experiments and so on. And if you read the notes, there are some more detailed explanations why this is the right order parameter to describe the nematic phase. So although this is a tensor because it is uniaxial, and the direction of orientation is arbitrary, we just know the particles will orient themselves, but in the absence of fields, this orientation is arbitrary. And so I can describe that by writing the tensor in terms of a scalar order parameter, which is really, well, it's the eigenvalue of the tensor corresponding, it's the largest eigenvalue of the tensor corresponding to, of course, because it is largest, corresponding to the direction of orientation, which I call n. And in nematic literature, this is called the director. And now this is something which is more complicated than a simple scalar, but this is quite doable. This is the order parameter. Once I have the order parameter, I can follow what I did for the magnet and write a free energy, an effective free energy, or a Landau. It's actually known by Landau de Gennes because de Gennes introduced this type of free energy to describe nematic ordering and nematic isotropic transition. So I have a local term that depends on powers, invariant powers of symmetric powers of the tensor, the order parameter, and then I may have variations of gradients of this order parameter and maybe some coupling with external fields. Here, I'm not going to look at non-uniform systems or coupling with fields, but it's just written in a more general form than the previous derivation, which was meant to be as simple as possible. Okay, so now the local term. The local term has a term that does not depend on the order, which is meant to describe the free energy of the isotropic phase. And then I have the invariance of the tensor. The invariance of the tensor, because this is a traceless tensor, are just traces, the square, the cube, and quartic. Because of course, if you look at it, these terms are invariant. They not depend on the orientation of the axis, and so I can have the second power, the third power, the fourth power of the trace of the second order tensor. Why do I have a cubic term here? Because this is not a vector, you see, and so having a cubic term here does not mean that I simply invert the orientations of the particles and I get the same free energy. This actually represents, because the order is a little bit more complicated, represents a state which actually is not equivalent in terms of free energy when I change the order. So I need the cubic term here. And so this is the square term, this is the quartic term, and it's non-trivial. Well, I mean, it's really, it's not too difficult, that's what I wanted to say, to show that the trace of the tensor is proportional to that order parameter S that I introduced here. So basically, this free energy will be powers of S squared, S cubed, and S to the fourth. Here, I've already made the assumptions that one term will depend on temperature linearly, the others will be positive, but they'll be constant as functions of temperature. And in the notes, there are some discussion of how to determine the signs of these terms. This one again is for stability reasons, and this one is to represent the what happens when I have this type of order. So this is sort of mentioned here, but you can find more details in the notes. Okay, so this is now the Landau de Gennes free energy, which is the equivalent of the simple magnetic free energy for the bulk uniform phases in the absence of external fields. But of course now, because of the cubic term, which cannot be removed, there's no symmetry operation in this tensor that will, there would be for a scalar, but not for the tensor, that would remove this cubic term, because it really does correspond to different orientations of the system, and those will correspond to different free energies. So physically, this term has to be taken into account. Okay, this is now the free energy as a function of S. I said these powers of the trace of Q can be related to powers, the same power of the order parameter S. This is always uniaxial nematics. And so I can have different curves here. They labeled by different, this is by changing the temperature, which is changing this parameter A here. The two are fixed. So first of all, I want to find out where the pneumatic isotropic transition occurs. And I'm using a value temperature, which is in terms of all these parameters that I've defined in the free energy. And the transition occurs exactly at when this temperature, written in terms of the model parameters, is 1. And this is the black curve. The black curve is here. You have a minimum at a finite value of the order parameter, and you have a second minimum at 0. This is 0. So this is the point where isotropic and pneumatic coexist. And then the other curves correspond to different temperatures. This is higher temperatures, and this is lower temperatures. At a higher temperature, then the pneumatic is no longer the stable phase, and I have an isotropic fluid, but there is still it still exists as a metastable phase for a range of temperatures. If I lower the temperature below the isotropic pneumatic transition, the opposite occurs. So I have now the pneumatic as the stable phase below the isotropic pneumatic transition, and the isotropic phase remains at a metastable state. And if I go lower and lower, I can get curves like these where the stability is lost on either side. And in fact, sometimes you really have to consider so this is the physically interesting region, okay? I don't know if let me see. Of course, I forgot to put the timer anyway. So I just wanted to say that I'm not going to go through these 2 slides because there will be many lectures on liquid crystals, the effects, and the elasticity. But the elasticity, that second term that depended on gradients of Q, can be expanded just like the terms in Q itself. And they have to be invariant, rotationally invariant. And here they are, they're sort of rather complicated, and you can write them down in terms of the direction or the director of order. And the only reason why this is here, this is a famous theory by Frank and Osin for the elasticity of liquid crystals, and the different coefficients here. And if you look at the way they sort of couple to different distortions in the liquid crystal, this is a splay, this is twist, and this is bend. And these are the low lying excitations from an ordered pneumatic phase. So again, we can see that Landau theory gives you a mesoscopic description. You can get the macroscopic equilibrium values of the order parameter and more. In this case, in this particular case, I showed how you can actually get the elasticity that has been derived by Frank and Osin from purely macroscopic arguments, thermodynamic arguments. Thank you very much.